Hello and welcome. Okay, my last main channel video is building this additional piece of circuitry for doing the level shifting and logic interfacing of the SD card. And so this video is about the programming. Now I included a shortened form of the programming in the main channel video, but the long form that I had originally planned to do is here, but it's like 40 minutes of footage and I think that would have been a bit too much for the main channel. Before we do anything else, define the chip select line. Now I've got the specifications for the SD card protocol, but unlike the other devices where we've got a fairly simple structure of set or read from a register, the SD card protocol is quite a bit more complicated. So what I'd like to do for this is follow a tutorial. Now I did a few web searches and this was a tutorial that came up as being quite well written, so I'll provide a link in the description. Now, as you'd expect, there aren't any tutorials out there for setting up an SD card on my custom CPU. So this one deals with talking to an Atmega microcontroller, and then we'll just adapt some of the code as we go. So first it deals with the connections. We've already made that. We've got a rough outline of the timing just for the raw data transmission and receipt. And we can look at this and see this lines up with SPI mode 0. And now this power up sequence is going to get interesting because this is the first thing we need to actually implement. Now I've got a new include file here, which I'm going to put the SPI interfacing logic in, and I'm going to keep the low-level basics in the SPI include file. So the first thing they do is make sure the card is deselected. Now that should be the default state of the line, so I don't think we really need to do this, but I want to try and mirror this code as much as possible. Now that's doing a 1 millisecond wait, which in computer terms is quite a substantial amount of time. Now, I don't have an easy way to do a millisecond wait, but I do have this function that waits in hundredths of a second, which is the precision of the RTC chip. Now we're making calls now, so we need to save the return address. We're definitely using the A register. And then we want 80 clock ticks without anything selected. Something I've been doing is adding some generic basic functionality here. So there's this simple 8-bit transfer functions I've added for each of the existing modes. We want to loop for 80 cycles. So that's 10 bytes of transmission. Okay, this doesn't actually look right because chip select is already disabled and it's just transferring stuff again. Okay, I'm a little bit suspicious of that bit of code, but let's reproduce the functionality exactly. So all commands are 6 bytes long, and despite the way this is all labeled, this is just sending 6 bytes sequentially. The first and the last have a value ORed in. Right, so we don't have enough registers to store that, so we're going to store it at a memory location. And before we move on there, I used C as well. If SI is pointing to 6 bytes for the command, LODSB will load it. We want to transfer 8 bits. So all the clock settings will be the same as the MCP device. This is good actually. This feels like we're able to translate the code in a fairly linear fashion. So call for transfer. We're having to send these in big endian order. That code is translated very easily. So we've got a flowchart here, and there seems to be a big branch in here between two different versions of cards, so we'll have to watch out for that. What I will probably end up doing today is implementing just the branch that the first of these SD cards I'm testing with supports, and then I'll go back and fill the other side in. So we need to send this go idle state. Now I have read that in SD mode the CRC is only relevant for a small subset of commands while we configure the system, so we can actually just read out ones from the documentation. Okay, so we've got this response format we need to worry about. All of our previous SPI protocols have been very simple. As this one, after sending a command, we're going to send FF and expect FF returned until it's ready to return data. Interesting. So we're going to need these 6 bytes, and we're going to need the response function. The count, and we need A. Right, so if it's not FF, we're done. Otherwise, we repeat until we've done it 8 times. And it looks like the failure is to return the FF. We're supposed to be sending FF. And we're returning the contents of A, so we don't need to save that. We do need to save B. Okay, so it's relying on the pull-up returning FF if there's no data. Okay, so we've got this function go idle state, so we're sending the command, reading the result, and then this interesting combination here. Right, let's do that. So same as we did before, we can just send that using the none transfer. Then they enable the chip select and send FF. It's easy enough. So here's the command 0 we want. And this is just what we're doing at the start in reverse order. This would have overwritten A. I'll just use one of my debug options to give us the return value. Right, I'm going to test that. Little copy paste error there. Okay, so that's returned FF, which is a failure case. Something to test easily here. Right, I'm going to output everything we get back. Okay, VAT transfer wasn't 0, but I don't know if that could possibly have made an issue because the chip select's not low. But it does make a difference. Okay, that's very unforgiving. We need to be extremely careful of this. Right, so we've got this far. Next step requires sending a command 8. Right, so different command to send. So this is our first branch point. We send the command and check the result. Let's do that. Let's get this read result 7 in. Now we need to return 5 bytes. This return 7 is actually 4 bytes of data in addition to the original base return. Okay, I'm going to decrement di 3 times, which will put it back to the start. So then the return will have the correct data pointed to by di. Or if there was an error, it will be garbage, which is the same as this does. Okay, what's next? Go idle did that. And so does send if command. I'm getting the impression that bookmarks all of the commands. So we do this, send a command, read the result, but that's potentially different from one to the next. That was a 1, this is a 7, although a 7 is a 1 with some extra work. Interesting. Let's see if that pattern holds true. There's probably some code merging we can do. So we're calling our new result command and sending command 8. Definitely feels like this could be in a generic function. We just need to save and restore that return. So the tutorial writer creates a function here which pulls apart one of these result values. I think I'll probably just stick with outputting hex for simplicity's sake at the moment. That 1 was confirming that we're in idle state. And this 5 has the bits for idle and for error set. Right, so we got an error back from that, and I think that's us taking this branch of the flowchart. So I'm going to try switching to a different card and see if we get a different result. Ah, yes, that worked. So for this card, we're on the other branch. That's a bigger card and a more recent one, so that makes a lot of sense. Version 1 or version 2. Okay, I'm going to switch back to the one that follows the simpler path. So we need to send command 41. Okay, so these bits are identical as well. So I'm just going to implement this path. Looks like this one's just got a couple of extra bits in it. Should be fine. So command 58. Read OCR. So result 3 is the same as 7. Shortcut it like that for now, if it's going to be the same code. So once again, we're seeing a lot of commonality here. Right, I'm just going to grab the whole of this function. That is that code. That is that code. Definitely want to merge that up. Let's get this step going first though. Print the result and the 4 bytes we get back. 0FF8000. Okay, for the microcontroller code, this is done in a quite a difficult to read way. So what we're seeing here is that this SD card supports lots of different voltages, in fact all of them. That ready bit is not set. Now, I'm not aware of anything not supporting 3.3 volts. Might be worth adding an error check in for it, but I'm just going to pretend that doesn't happen for now. We should test for an illegal command, but it doesn't look like we need to check for anything else. So if we get there, we're at this point ready for this loop by the looks of it. Right, now before I go on, I want to simplify the code. Read OCR, send ifcond, go idle, they all have this block of code before that. So instead, I'm going to call that begin and stick that at the front, since we're always doing that, then sending a command. And likewise, this bit always happens at the end. Call that SD end. And because we save and restore A inside there, we don't need to do that anymore. Okay, so this I like. All three functions got much simpler. Quite a bit smaller as well. Let's double check what the code does with the other card. Yep. And without a card. Okay, this is a bit hacky, but I'm just going to write a temporary function to output 4 bytes from DI, because it looks like that's just going to be handy for debugging this. And we'll put DI back where it was. Okay, it's a bit neater. Right, so now we've got this ACMD41. That's everything we've done. So we're down to here, and we just need to do this application command 41 and loop on that until either we declare an error or the card is returned as ready. So to send the application command, we have to send this command 55 first. Let's set up the data for those. I'm seeing a lot of commonality between some of these functions beyond what we've already done. Now, I've just noticed that I'm not saving and restoring SI when I should be. App command is basically just a prefix that expands the command space. Makes sense? So we've got two variants. The most common one is a begin, an end, and a read res 1. So that can handle pretty much all of those. Might need to worry about this failing, in which case I assume it won't be valid to send that. Let's see what the tutorial says. Okay, this line I'm not so sure about. Yeah, so on this path we don't need to do that, we just need the ready status. And on this path we need to do that check to just confirm what language you're speaking. If my advanced reading on the documentation is right, I think this just changes the way we have to index memory on the card. So we'll need to take a note of that once I actually support this code path. So if it fails, I'm just going to print that out. Ten milliseconds is 1/100th. This doesn't actually seem to have a break. I can check the code again. Must have overwritten that by accident. Okay, so that looped 3 times. So that'll be 3 1/100ths, and then we got to the end of the flowchart. So we don't need to do that for this type of card, but I do need to implement the other path, but I'm going to save that for later. Right, so now I've moved all of that work into just an init function. I might want to convert this into something I can put in my main debug library. Just double check that still works. Right, so now we're getting to the real interesting bit. So we've finished the initialization, and now we're going to try reading a block of data. Command 17, read single block. Now I want an upper limit on the size of SD cards I'm going to support. So block ID in 16 bits. What does that give us? So we 2 to the power of 16 plus 9. So that would be 32 megabytes. That's not big enough. So if we do ABC as the block, that will give us 256 times that. 8 gigabytes. I think that's more than we need. To be honest, 32 megabytes would be big enough, but I don't have any SD cards that small. The main ones I've got here are 128, so I need to be able to support those. So this is the standard preamble, but we need command 17 read block. So it's pretty much all the standard preamble. Right, so we're reading this up to max read attempts. Max read attempts is a strangely specific number. I think I should trust it though. Okay, so let's print that response code. I'm going to try and do it up to 1,563 times. If we have a response, we're interested in seeing if it's FE. In which case, we need to read the data in. Now we need to do this 512 times. I'm actually going to do it twice in that loop, because it's really easy to make something loop 256 times. Okay, if I'm not mistaken, that's the code. Now we're not doing anything with the block index. The read block command just has a big 0 there, but I want to see if this code is working before we mess with that. That was a very hidden typo. Right, let's ask it to write to address 7000. So a block is 512 bytes. So that would be a whole sector, and that's currently initialized to FF. So that has not changed any of the data. Okay, that's interesting. My init function is now failing. It's good to know we can reset it just by taking it out and putting it back in again. So that gets a 0. So that should be if not equal to FF. We've got a response to check. Reset it again. That presumably got a series of FFs, say the data wasn't ready, and then must have got the FE. Okay, still no data change there, assuming address 0 isn't all Fs, which would be a bad coincidence, and an invalid format. Okay, I want to see what the return value is. And that is the FE. So it should be hitting the read loop. I think I'm just writing it to the wrong place. It's behaved exactly the same, but now if we check the address 700 hex rather than decimal, it's no longer FF. There's some data. I have absolutely no idea if that's correct or not. So the first sector of a block device should be the partition table. It would probably take a while to write some code to decode that, but I'd like to save that for a future video on file systems. But for now, I want to read block 336 because I have written a small file to this SD card and I've used a Device Explorer program to go through and work out that the first sector of that file is in block 336. So this command 17 read block is currently hardwired to address 0. And ABC is the block. Now the big difference between standard and high capacity SD cards is the index in a high capacity card is the block number. So we can just take ABC and put it in the lower 3 bytes of the read block command. But for the regular capacity cards, it's the byte index. So we need to multiply ABC by 512. Clear the carry flag. Now this will shift left by 1, which will multiply it by 2. And of course, if we store it with a 1 byte offset, we get the extra multiplied by 256 free. So we want to store A, B, and C in the top 3 bytes of the command. And then that final dec SI takes it back to the beginning, so I don't need that. Now when I come to optimize the read functions, it might be worth just doing a custom send of the command without needing to store it and then send it. We can optimize this loop a lot just by writing a custom read loop. But let's give that a try. Ah, look at that. Oh, that's awesome. So we have initialized the SD card and we have read a block of data from it. And that block of data was actually written on the PC. So, we're kind of ticking a lot of boxes there. I definitely need to do more work, particularly on the initialize, give it some better error handling, probably on the read as well. I need to support high capacity SD mode on the read. So the initialize will need to store some state off. But the initialize and read as an external interface is 2/3 of what we need. We want a write as well. Need to move those into my SD library as well. Okay, so write block, I'm going to use SI as the source location. It's the same ABC for the block address. If it's worked, that will read the data we've written back into address 7000 from wherever it was, instead of the data we saw before. Now, at a guess, code is going to be very similar to this. So write block is 24. Okay, so this is exactly the same, but sending the different command. We need to send a start token. So that start token is the 0FE. I had to go and read the header file to get that. It also means that's the start token. Now we write the data out. And that will read a byte from SI. Okay, so we actually just flat transfer the data. I'm going to need to dig into the documentation and see if I can work out where these magic numbers come from. So we are looking for this being anything other than FF. Let's just do a debug print of that, but what we're actually doing is we want to AND it with that and then compare it to that. All right, definitely need to define for that. Okay, is that everything? Okay, so if that's worked, and we did get a 0 return. No, that's still the old data. From outputting return values the way I am, they're difficult to distinguish when I'm using like debug A lot. So we've got a 0, 0, an E5 and a 0F. So pass through there, okay. I've written the 512 bytes. The right response is the next value that comes out, E5. And then we're looking for 5 after ANDing it with 1F. It's indeed 5. Let's check that code again. Actually, I suspect the max write attempts value is the 250 milliseconds over their clock rate. So we do get a bunch of zeros and then a 3. That feels like it worked. That's the correct data. It has worked. Oh, awesome. Okay, why didn't that work first time? Did I have a small mistake that I accidentally fixed? Or have I got a bit of error checking I need to add in? That seems likely. As our final check, I'm going to put this SD card into a reader. So that is the text file I created. Haha, awesome. The one thing to note there is we're not seeing the multiple replications of that string that we actually wrote, and that's because the file was only a few bytes long for the original message we saw, and I've not done anything at the file system level to tell it that there's more data there. It's just reading in the length of the original text file I created. But we have successfully written some data to an SD card on the PC, read it on our SD card reader hardware, overwritten it with our own data and read that back in on the PC. That is very, very encouraging. Okay, back to the main channel for the final conclusion, but I would mention just while you're here that if you don't want to mess around with this circuitry, there are modules around like this which do the level conversion and allow you to plug an SD card in. This one's for micro SD. And be careful of these. This one's for a full-size SD card, but the logic here is just a few resistors, and I don't think it's quite as complete. I think it relies on the output lines being open collector, and so this is more suited to a microcontroller than the kind of circuitry I've built here. So I don't think you want to be trying one of those. Goodbye.